we've got one more thing to tackle when we're talking about integration by substitution, and that is the really important thing of what happens when we have limits. So far we've only done indefinite integrals, and as a result, when we get our answer in terms of u or theta, then it's absolutely fine and I can just swap those variables back. But when we have a definite integral, there's an extra little barrier that we need to address. So let's have a quick look at these two examples, and we'll talk about what that little extra step is as we go. We're not told the substitutions this time, but they are actually much more straightforward. Then there's no awkwardness here. If we pick inside the brackets u equals x plus 1, then we're going to make some good progress on this one. It would be useful to know what du by dx is, and that's just 1, and that means that du can be replaced with dx. And it would also be useful, I've got a u plus 1, I've got an x plus 1, sorry, I've got a dx, I also need to know what x is. So it's also helpful just to note that x equals u minus 1. So now we can sort our whole integral out. So the integral of x times x plus 1 cubed dx is the same as the integral of x is u minus 1, x plus 1 is u, so u cubed, and then we can just swap the du in. And it would be good to expand those brackets out, so I have u to the power 4 minus u cubed, and therefore we can integrate this as just a polynomial, so I end up with u to the 5 over 5 minus u to the 4 over 4 plus some constant. And final little thing I can do is I can switch this back over to being in terms of x. U is x plus 1, so this is going to be x plus 1 to the 5 over 5 minus x plus 1 to the power 4 over 4 plus c. All good so far, nothing surprising. When I add limits into this, however, when I add limits in, we need to notice something. If I say, well, okay, what I've got is u to the 5 over 5 minus u to the 4 over 4 between 0 and 2, because those were the limits we were given in our original, this needs to somehow be exactly the same as u to the 5 over 5 minus x plus 1 to the 5 over 5 minus x plus 1 to the 4 over 4 between 0 and 2. These should somehow be exactly the same. But hopefully you can see straight away we're going to run into a problem, because I've got two completely different solutions, a u1 and an x1, for the same integration. And if I substitute the same values into both, I'm clearly not going to get the same answer out of both. So this 0 and 2 that belong with the x1, they absolutely have to be fine, because they came from our original integral, which was in terms of x, and the limits for that integral were 0 and 2. So our problem must be with the limits on our u version of that definite integral. And they are actually a really simple problem to solve. In fact, there's two ways of solving it. One way is just to go back to the x version, revert everything back to x's, and substitute the x values in. And that's absolutely fine. That will always work, no problem. However, sometimes that's actually quite a bit more complicated than sorting out the u version for your definite integral. In this case, it's a little bit more tricky because I just end up with some slightly bigger numbers to take powers of. It doesn't make a massive difference, but it's a little more awkward. However, if we could keep everything in terms of u, but recalculate these limits, that would be kind of helpful. So what we tend to do is just draw a little table of limits down here. So originally my limits on x were 2 and 0. And we know u is equal to x plus 1. Well, if u equals x plus 1 and x is 2, then u now must be 2 plus 1, which is going to be 3. And for the other limit, u is 0 plus 1, which is 1. So instead of having these original limits, we adjust our limits to 1 and 3 because we've changed our variable from x to u. So we have to adjust those limits as well. And now that I know this, I can just substitute 1 and 3 into this u version. So my final answer is going to be 3 to the power 5 over 5 minus 3 to the power 4 over 4, subtract 1 to the 5 over 5 minus 1 to the 4 over 4. And at this point, this is just a calculator question, which is not terribly difficult to do. So 3 to the 5 over 5 minus 3 to the 4 over 4. I should probably put some brackets in there. Minus, big brackets, 1 over 5 minus 1 over 4. And we get 142 over 5 as our final answer. There's no big surprises there. And we could obviously have also substituted those values into the x version and we'd have got the same exact thing. It's also worth remembering that you've got a class-based calculator that does integrals. So if I just hit the integral button and type in x brackets x plus 1 between 0 and 3. Oh, it helps if I put my cubed in. And hit equals. It also helps if I put the correct limits in, because I'm not paying attention. I get 142 over 5. I get the exact same thing. And this specifically says use substitution to evaluate. So you have to do the work and demonstrate that process, but you can use your calculator to double check that what you've done makes sense. The other thing to remember, of course, is that the calculator does everything numerically, so it won't always get the exact answers that you would get from doing it by hand algebraically, particularly when pi and surds end up being involved. Okay, so we can do this by substitution, but we need to just remember that our limits are changing because our variable is changing. So we need to adjust the limits accordingly. So for the second one, let's just work through this as well. Again, we're going to just pick the obvious substitution of 1 plus sine x. It's obvious because it's kind of within the surd there, and if I swap that for u, I have a simple thing to integrate. What that means is du by dx is just going to be cos x, and handily that means du is equal to cos x dx. And actually I don't need anything else now because I have a cos x dx right here and I have a 1 plus sine x right here. So I can swap this integral. So the integral from 0 to pi over 2 of cos x root 1 plus sine x dx is equal to the integral of cos x dx becomes our du, and 1 plus sine x becomes our u, so it's root u du. But I need to just reorganize my limits now. So again, let's just think about what happens here. When I had x, my limits were between pi over 2 and 0, and u equals 1 plus sine x. Notice that we're using pi over 2, so we're definitely in radians. So as long as my calculator's in radians, I can just tap that in and check what's going on. So what is 1 plus sine of pi over 2? It's 2, because sine pi over 2 is 1. So my new limit is 2. And similarly, you might already feel quite confident about this one. Sine 0 is 0. But it's always worth checking these things on the calculator just to make sure. So my limit's gone from pi over 2 and 0 to 2 and 1. And at this point, I'm ready to integrate. And actually, the integration is really, really simple. So this is u to the power half. So when I integrate it, I get u to the 3 over 2 divided by 3 over 2 plus some constant. But because I'm doing a definite integral, I don't need my constant. I just need my limits of 1 and 2. And u to the 3 over 2 divided by 3 over 2 is going to be the same as 2u to the 3 over 2 over 3. And I'm going between 1 and 2 here. So this is 2 times 2 to the 3 over 2 over 3, take away 2 times 1 to the 3 over 2 over 3. Again, calculator if you want, or you can work through this whole process yourself. But what we're going to end up with is 2 times 2 to the 3 over 2, all divided by 3, take away 2 times 1 to the power of 3 over 2, all divided by 3, and we're going to get this decimal number. What's my calculator done? It's not done everything exactly because it's stupid and it doesn't know any better. So this is the point where your calculator has limitations, and if we plugged the original integral into calculator, it would also cause this same problem. It would not sort everything out properly. So it's well worth just remembering this. Calculator is useful as a tool, but it's a tool. It doesn't do all the maths for you. So 2 to the power 3 over 2 is the square root of 8. So this is 2 root 8 over 3, and then this is minus 2/3. And actually that'll do as an answer, or you could pull these two together if you prefer, and then get 2 root 8 minus 2 over 3. Root 8 also tidies up ever so slightly, because root 8 is 2 root 2. So we could write that as 4 root 2 minus 2 over 3, and we're probably going to stop there. It's not going to get much tidier than that. And obviously we can confirm this on the calculator. So 4 root 2 minus 2 all over 3 is, boom, it's exactly the same decimal as we got a minute ago. But you're not going to get that decimal or that exact value from playing around with all this numerically on the calculator, because it's not perfect. It's just approximating things. A little summary. There's a couple of really key points you need to pay attention to when we're doing substitution. Obviously, we need to get rid of all the x's and put them in as u's or thetas or whatever it is. But don't forget, you also need to substitute the dx and replace that with a du or a d theta, depending on what your new variable is. And if we have a definite integral, you need to change the limits of that definite integral as well, or convert everything back to x before you plug numbers in and calculate values. But generally speaking, changing the limits is simpler and quicker than converting everything back, because generally speaking, we do this so that the integral is simpler, and therefore the answer will be simpler than the converted back version. That's everything on integration by substitution, but it is a huge topic with an awful lot of variation in the questions that you can be asked. So your job now really is to do as much practice on this as possible so that you have the experience you need to recognize when substitution is useful, which substitution to use.